Okay, so we're going to do the quiz at the end today. So that way there will be more examples and you should feel more confident about it. So let's just kind of review what we're talking about. So remember when we organize data like this, we put the value of the variable on the x-axis. So this was the price of DVD players, number of TVs in the household. I don't remember what that was. But we put the value of the variable, and then there's different ways that we can then kind of display visually where most of the data is, or what we call the frequency, right? So 3 DVD players were $219, and so the more that gets stacked up here, then obviously the more data that's there. So that's what we call frequency of the data. And then this kind of stem and leaf plot is just it's vertically. So if we turn it on its side, it's the same thing. So what we get is a distribution of the data, right? We get a distribution of where most of the data is occurring and where not as much data is occurring. And that's the idea of frequency. And so then we take the tops of those, we're stacking up the data, right? Or we're measuring frequency. And so if we take the top and draw a curve through it like this, we end up with curves. So we get a curve that's mapping out the frequency of the different values of the variable. So most people have 1 or 2 TVs in their house. So that's where the curve is the highest. And not very many people have 6, 7, 8 TVs in their house. So the curve is lower there. Okay? So we get all these different shapes, right? We get these shapes of these curves. And so in this chapter, we're looking at what's called the bell-shaped curve, or the normal distribution. What does it say? Most frequently, the data ends up around the middle. The further you get away from the mean, or from the middle of the data, the less frequent observations occur. And then we saw this relationship with then area under the curve. So if we were to find, if we wanted to know what percentage of college women were between 60 and 63 inches tall, we'd come over here and we'd look at from 60, you've done these before, from 60 to 63. And we would add these up, right? We'd add that and that and that. We'd add up those 3 percentages, and this would give us the percent, or the probability of a woman, a student, whose height was between 60 and 63 inches. But those numbers, see that 0.45, that 0.7, could also be thought of that 0.45. We see that as the area of this rectangle right here. And then the 0.0757, that's the area of this rectangle. And the 0.1170 is the area of this rectangle. So what we see is this relationship between relative frequency, or probability, and area underneath the distribution curve. Right? So if I took the area underneath the distribution curve between 60 and 63, that would be very, very similar to adding up these 3 numbers. So this idea of area under a distribution curve can give us percent of the data, or probability, within that interval of the variable that we're choosing. Okay, and then what we saw was that all normal distributions can be standardized, right? Standardized to the standard normal distribution. And it's all based on what? So what is the standardizing factor about all these curves? That ends up being our x-axis variable on the standard normal curve. So what are these numbers? What do they mean? What are they? Yeah, so this is key. So though, when you get a z-score, those are standard deviations from the mean. And that is what, so we can take any normal distribution and we can change, using its mean and standard deviation, we can change it into a z-value. And the z-value is always a standard deviation from the mean. And so the standard deviation is this kind of universal basis for percentage of the data, or relative frequency, so that no matter what mean and standard deviation you have, standard deviations will always contain the same portion of the data. So if I go from the mean, say, to 1 standard deviation above the mean to 1 standard deviation above the mean, there was 1/2. And here what the mean is 1. So here's, now in our standard normal, the mean is 0, standard deviation is 1. So all those regions that I've just shaded in, they all have the same area. And they're all the percent of the data from the mean up to 1 standard deviation, or what did I do? 1 standard deviation above the mean. So all those have the same area. So we can use just this one then to relate to any standard normal curve, right? So that's why we can always deal with the standard normal curve, because we know that the areas and relative frequency are the same for that one or for any, based on number of standard deviations. So all those areas are equal because they're all the percent of the data from the mean to 1 standard deviation above the mean. So this says that same thing. Equal areas, right? Equal areas. A normal curve with mean, mu, and sigma, and a standard normal mean with the corresponding z-scores. Of course, these are the corresponding z-scores to A and B. Same area. Okay, so don't try to write all these down. We'll just read through them. So the total area under the standard normal curve is 1, because 1 is all of the data, right? It's all of the data for a particular data set. So it's like 100%. All right, the standard normal curve extends indefinitely in both directions, never touches the x-axis. Standard normal curve is symmetric about 0 because that's the mean of z-scores. And it's a mirror image left and right. Okay, so it's reflected across that 0 line. And almost all of the area, we talked about this before and we'll mention it again, almost all the area lies between -3 and 3. Okay, so it's like 99.7% of the data will be within 3 standard deviations on either side of the mean. Okay, so here's some just warm up. So what are we saying by this? If we're saying, so this z equals 1.23, what does that number mean? Z equals 1.23. She's saying we're talking about 1.23 standard deviations above the mean. Is that right? Exactly right, okay? And so then that transfers to any distribution, any normal distribution that we have. If the mean is 1,000 and the standard deviation is 40, then it'd be 1.23 of those 40s above 1,000, right? So it'd be 1.23 of whatever the standard deviation is above whatever the mean is, okay? And so by finding this area then, what are we finding? By finding that area, what is it that we're finding? Yeah. What probability? Okay. But for this setup right here, If z equals 1.23, what exactly is that area? He said it's a probability. That's true. What probability is it? She said it's the probability that a data value falls below 1.23 standard deviations above the mean. Ashlyn likes it. Did she get it? Is that right? Exactly right. So this is the relative frequency of all the data less than 1.23 standard deviations above the mean. So it would be also the probability that if you picked an observation randomly, you would get it would be less than 1.23 standard deviations above the mean. So let's guess at what that is. Just guess at what that area is. What would you make a guess as to what that area is? Miguel, what would you guess? $65 what? 0.65. He says 0.65. No, we're going to do that in a second, but we should be able to look at that and say it's going to be around something. So did you already look? No, okay, so you don't want to answer. So what do you think? Okay, 0.65, 0.8, 0.75, something like that, right? It looks like more. This would be a little bit less than a quarter. So I'm thinking 0.8 would sound pretty good. Okay, so now how do we know that for sure? So then we go to our chart, right? And so the chart. Anybody need a chart? Okay, two more there. All right, so on the left side of the chart is for z-scores that are below the standard, z-scores that are less than 0, negative z-scores. Okay, and that will give you the area to the left. And then the right side of the chart will be for z-scores that are greater than the mean, and it gives you the area to the left. These areas are always to the left. These are always to the left. So what's our z-score? So we're going to look at this one on the right side of the chart, and we're going to look for z equals, is it 1.23? So we'll round that to 1.2. Wait. No, sorry. So you can look at 1.2 and then 0.03. So 1.2 right here. So kind of it works the same way as a stem and leaf plot, right? So our stems are down here like this, and then our leaves are across there. So we're combining the 1.2 and the 0.03 to make 1.03, and is it 0.8907? Yeah. So that's the z-score for 1.23. For z of 1.23, this is the area beneath the curve. 0.8907. And so how do we interpret that number? What does that number mean? 0.8907 is what? Right, so it's the probability that an observation from this date, whatever the data set is, if you picked one at random, it's a probability that you'd be below 1.23 standard deviations above the mean. 89% chance. Okay, so let's do, then if you wanted something to the right, then how would we find to the right? So we got a z of 0.76. 0.76. So you can go in here. Again, that z-score is over here, greater than the mean. So we're going to go 0.76? So we're going to go to 0.76, like this. And we get 0.7764. Okay, 0.7764. So is that area that's being shown? 0.7764. No. So Kesman, why not? What do I have to do? Right. So the total, all the data is 100% or 1, and that's the total area under the curve. So if we want this area falling greater than 0.76 standard deviations above the mean, then we've got to do 1 minus that. Oh, we should have guessed first. That's okay. So is this 0.2236? The area, so it's not that the data set is going, we're asking for the area to the right, or we're asking for the probability that you're greater than 0.76 standard deviations above the mean. Because that 0.7764 is this area. So now we only want the relative frequency of all the data greater than 0.76 standard deviations above the mean. Okay? And so finally, so what's the roadmap? Now we want this area between these two. Between these two. So we need kind of a roadmap to figure out what all that area is. So Trevor, what do you think?
Why don't you do the thing for both numbers?
Okay. All right, so if we do, so don't look at your chart. Don't look at your chart. First of all, let's predict. So make a guess as to what this area is. Can we make a guess? What do you think? Rachel, can you guess what our answer is going to be? Something close to what our answer will be. Was it? She wants 0.4. A little bit less than half of the area is in there. Another guess. 0.6. What's that? Your guess is 0.63. All right. Okay. So yeah, to me it looks like more than half of the area. To me it looks like more than half of the area. So maybe 0.6 to 0.7. So the 0.63 might be good. Maybe have you already done it? No. Okay. So our guess is the answer is going to be about 0.6 or 0.7, or 60 or 70% probability that an observation will fall between 0.68 standard deviations below the mean up to 1.82 standard deviations above the mean. So what is, everyone look up, what is the corresponding area for z equals 1.82? Everybody find it. What's the corresponding area for z equals 1.82? He said 0.09656. Did everybody see where that comes from? Everyone able to find that? We good? Okay, cool. And then what about negative 0.68? Everyone find it. Make sure you can do this. 0.7517. No. Uh-oh, you're getting challenged there. Try again. 2483. There's some nuts. So then how do we use these numbers to get the area that we want? Yeah. Right. So this 0.9656 is from here where? All the way to the left. So we've got all that area. is the 0.9656. If we want just the area between them, then we want to get rid of all of this area. So we're taking all the area from here over and subtracting all that area. That gives us the area we want. So it's going to be 0.9656 minus and it's 0.71 something. 0.7 what? 73? Okay, so our guess was decent, right? We guessed from 60 to 70% of the data falls in that range. It was 0.7173. Okay, anybody have a question? So the rest of it, so I've got mostly examples that you can work on before the quiz. But so this is most of it, right? Understanding that what we talked about so far is most of the deal here. There's a little bit more I want to show you, but.
Oh, I didn't really get the Venn diagrams last time.
The Venn diagrams?
The Venn diagrams.
Yeah, I didn't plan to go over those again. Sorry. But maybe if I have a moment to help you while everyone's working on stuff. Was there another question over here? Yeah. I'm sorry? I don't understand your question.
Can I have this score from 3 points? Or maybe 4.5?
For 4.5. Okay, so you're talking about way out here?
Yeah, or does it go up to 3.9 as it's shown on the
Right, so why does it only go up to 3.9 and not any higher? Yeah, so in terms of to 4 decimal places, then you get, if you're rounding to 4 decimal places, by the time you get to 3.9, you just round to 1. If you were carrying it out more and more and more decimal places, you could go higher than be 0.9999999. Does that make sense? So, but if we're rounding these areas and these frequencies to 4 decimal places, when we get to 3.9, then everything after that gets rounded to 1. So that's why the chart stops. Does that answer it? Okay, so let's do some practice here. So not all of these. Let's just do one. How about, it doesn't matter. How about A? So we'll just do part A here. And then part B. Or no, A. Again. So do part A, just part A of each of these, just for practice. So part A is a little bit different here. The second one is a little bit different. So we're saying either to the left of negative 2.12, or to the right of 1.67. So I'll leave that up to you to kind of deduce how you'd find that. You can do it. Just a variation on the stuff we've done before. And then remember, just if you want to make these diagrams as kind of a rule of thumb, you see how it's pretty flat here on the curve? And then it's pretty flat down here on the curve? So at the kind of in the middle of that where it's the most curved is pretty close to 2 standard deviation. So this is about z equals negative 2 right here. Where it's kind of the most curved. Where it's the most curved right here is about, that just helps to make good sketches. So that's equals 2. It's just a little trick, okay? It's just to help you with sketching. So I'll just make a lap around and see if you have a question, you can catch me. We'll just work on these two. If you get an answer, then compare it with someone around you. So anybody have just the final answer for part A as a means of checking? Anybody got part A yet? Final answer. Say it again? So as your final answer, you should get 0.9105. I see lots of nods. Anyone have a question about that? How about the second one? So you have to be a little creative. I didn't do an example exactly like this. Question? For part this first one? Because the z-score for 1.44, so I'll do it in red. So 1.44 is something like around here. Okay? And you got that z-score. What does that represent? That number that you got for when z was 1.44. What does it give you relative to the curve? What's that? Which probability? Where? Relative to 1.44. Below. So it's this whole, so when you look up 1.44 equals z in that chart, it's going to give you all this probability. All that area. Or the relative frequency of all the data less than 1.44 standard deviations above the mean. Then we do negative 2.8, which is negative 2.18, which is right about here. And you looked up that z-score. What did it give you? Or what does it represent? All the area where? Where? No. It's both sides of the chart is to the left. So both sides of the chart. See, if you look up here at the picture up here, so if you have a z-score that's greater than the mean, it's giving you the area to the left. And if you have a z-score that's less than the mean, it's giving you the area to the left, always. The whole chart gives areas to the left, even if z is left of the mean. Is that cleared up? So therefore, when you looked at that z-score for negative 2.18, it gave you this area. So how are we going to get the area in between? You see that you'll subtract? You take all the red area, which is everything from here all the way out, and we don't want that, so we subtract that because the area is. Okay, how about an answer for this one? I got 0.0645. Someone else get that? 6450? Oh, 0.0645, sorry. Got it. Questions on that? Did you figure out how to, so most of you did. Any questions on how you do that? Yeah. It doesn't matter. So unless it specifies. If it asks for a percent, then you write it as a percent. So what percent would this be? What percent of the data? So this is finding the area. Since the total area is 1, then you have to leave it in decimal form if it's in the report area. But if they say what percent of the data is such and such, then what percent of the data would qualify here for this or this? 6.45%. So it depends on how they ask it. Questions on these two examples? Last chance. Yes?
In order to find any data like on the right side
Mhm.
of any line, we should just subtract it to
Okay, so if you do z for 1.67, what will it give you? This area from here where? All the way over, right? And the total area under the whole curve is? So yeah, so under the whole curve, everywhere, that's all of the data. So that's 1. So now if we want this area here, that's what you said. Because you're going to have the whole, all of it, minus everything to the left, which you get from the table, leaves that. Yeah. So what you said was correct. What's that? About which? Okay. So what was the z-score for negative 2.12? 0.0170. Okay. And now what was the z-score for 1.67? 0.9525. So to get this answer in general, what we're gonna do? We're gonna add those two areas together, right? So we need to get. We have this area. That is that area. But what's this area? How do we get an area to the right of a number? It's not that, right? It's gonna be 1 minus that. So this is one of the advantages to making a guess, to actually thinking about the numbers that you're looking at. If you would have, before we would have done any of the chart stuff, if you would have guessed at this, what would have thought? What would you say? 0.1, 0.2, something like that, right? So we're expecting 10%, maybe 20, probably more like 10% of the data. So then when you get a z-score of 0.9525, you should be like, okay, that's not this, right? That's definitely not this. So, oh, that's right, I have to subtract from 1 to get the rest of the area under the curve. So I'm going to subtract this one from 1, and then we're going to add those together. You good? Okay. All right, so here's, before we get to some more examples, so here's the opposite. So z of 0.025, z alpha notation. Z 0.025 means we want the z-score such that the relative frequency above that z-score is 0.025. So this is a little, you have to be careful, because the z alpha, that alpha number refers to area above the z-score that you're looking for. Okay, so this is working backwards now. So we're working the other way. We're given an area, but it's the area above, and then we want to figure out what the corresponding z-score is. So how are we going to use the chart to do that? How are we going to use the chart to figure out what z-score has 0.025 area above that z-score? What are you going to look for on the chart? Okay, so careful. What does the chart tell you? It tells you area to the left. But a z alpha, that alpha is talking about area to the right. Subtract it from 1 and get this area first. So what is that area? Point 975. Okay? So the area to the left of this z-score that we're looking at is 0.975. So can you use the chart? Now you're working backwards. You're given the area, you're trying to find the z-score. Just find the closest one that you can find. Say it again? Yeah, by symmetry you can do that. Yeah, it's okay. All right, so you go to 0.975 and what'd you get for a z-score? 1.96? So we got that 1.96 was the closest z-score that gives you an area of 0.975. Agreed? Does it make sense? All right, try this other one. So find z of 0.05. What did you get, Cosmin? 1.65. Someone else get that? So first you look at that area, which is that area is 0.95. And the corresponding z-scored working backwards from the chart. Now you're looking in the middle of the chart for that area, and then you're figuring out what the corresponding z-score is. Question? Yeah.
Do you use 1.645 or do you go the distance on these like units or because like 1.64 is 0.9495 and the next one up is 0.9505.
Yeah, so you can just take the one that's closest. Like on all the homework, they're asking for round to 2 decimal places. So whatever one is closest to that.
What if it's like right in between?
Right in between, then you got multiple attempts on your homework, right? Try the one lower. If it's not right, try the one higher. I'm not sure how they have it, but it would be right. If you wanted to be more precise, then it'd be what 1.645. Like you're saying, if you want to do 3 decimal places on z, it would be right between them. Would be a closer estimate. Yeah.
When do we find average of those? Like, because you said like to guess if it's not to guess but to take mark them. Like,
Yeah.
if it's in between 0.04 and 0.05, like on the chart. And on the example last week on Monday we did with the average of those. Do we always do that, or like?
Well, so actually, I think all the examples you won't have to do that,
Okay.
but it was just a way of getting an answer kind of quickly, just to look halfway between, right? So if it's halfway between 2 z-scores, then it's going to be somewhere halfway between those 2 areas. That's all I was doing. Does that?
So for homework we didn't have to.
In the homework, you don't have to do any. It's called extrapolation. You're looking for values that are in between values that you're given. But I don't think you have to do that on the homework. Yeah.
So I'm a little confused. How do you get the z-score? Are you gonna get the area and how do you get the z?
So you're working backwards. You're going to look in the middle of the chart. You're going to look for where it's closest to 0.95. So what is the number that's closest to 0.95? 0.95. Is this exactly halfway between? Is that what happens?
Yeah, it's over.
All right. So what are the two numbers that you find? 0.94 what?
9495
9495.
and 0.9505.
Okay. So these are two numbers. Do you find these 2 numbers in the chart, Scott? For areas? You're looking for those 2.
Where is 0.94?
You just got to look. You just got to look real carefully until you find it. I don't know. So this, but that comes after. You got to find this number first, and then get the 1.64, right? So did you find it? Okay, and so then you're working backwards, and you're looking to the left and up to get what that would be, and that's 1.64 for a z-score. See that? So if you look to the left, you see 1.6. If you look up, it'll be 0.004. And then same with this one. On this one, it'd be 1.65. So you're doing exactly the opposite as what we did before. You're starting in the middle, and you find the number you want for area, and then you go like this.
Yeah, I got it.
Okay. All right. So 1.96. So they split the difference, okay? They said 1.645. They went halfway between. Okay, let's do a couple more examples, and we got to talk about percentile, and then we'll take the quiz. So try this. So here's people having IQs between 100. The mean for IQ is 100, and we're looking at standard deviation of 16 is the mean standard deviation for people's IQs. So what's the probability someone has an IQ between 115 and 140? How are we going to do that? So all we need to get is what? We just need to get the corresponding z-scores, and we're home free, right? We know how to do this. So we need the z-score for 115, and we need the z-score for 140. And once we have those z-scores, then we know that area between 115 and 140 will be the same as the area between those z-scores. Same area. So same percentage of people. Okay, so then I'm going to set you loose on this page. So let's just talk about percentile. So before you do all the crunching here. 40th percentile means that observation is greater than 40% of the data. So this means the observation that's greater than exactly 40% of the data. So what area does that translate to? So if we're looking for an observation that's, first of all, will that be an observation to the left of the mean or to the right of the mean? Left or right is greater than 40% of the data.
40% lower than the mean, but the area would be to the right.
I'm asking where the observation would be, to the left or right of the mean, if 40% of the data is less than that observation. Left, right? It'd be like something like this, something around here. And so how does if 40% of the data is to the left of that, how does that relate to area in our z-chart? What would we look for in the z-chart? .4. If it's greater than 40% of the data, then we're thinking we want an area of 0.4 to the left. That's exactly what that means. So we're going to look for this area to be 0.4. That's what the 40th percentile means. Because it's by the definition of what percentile is. I'm telling you the definition of percentile is, it's the 40th percentile. It's the observation that's greater than exactly 40% of the data. So we want an area of 0.4. Is that clear? So we want that observation that's greater than or 40% of the data. So that means 0.4 has to lie to the left and 0.6 to the right. So that's the definition of percentile. So what'd you get for that? So you're looking for 0.4000, and that gives a z-score of? It's the other way around. You're given the area and you want the z-score, right? So percentile will give you area, and we want the z-score. So what z-score corresponds to 0.4000? What's the closest one you can find? Negative 0.25 is what Jason says. Agree? Negative 0.25. Everyone find it. Okay, so now, this was finishing times, minutes, number of minutes and finishing times in a run. So, what was the finishing time of someone at the 40th percentile? So again, it just goes back to what's the meaning of this number now? Z equals negative 0.25. You know what that number means? This is easy to calculate. What does that number mean? Negative 0.25 what? Standard deviations below the mean. So if our mean is 61 minutes, and the standard deviation is, how many minutes is it? 9 minutes. Then what time in the race is, how would you calculate the time in the race that's 0.25 standard deviations below the mean? What would you do? You're trying to figure out what time in the race is 0.25 standard deviations below the mean of 61. Should make sense. What would you do? You would take 0.25 of 9 and then do what? Subtract it from 61, right? So you want this, if this is a portion of a standard deviation, you're going to take that portion of the standard deviation, you're going to start at the mean, and you're going to go down 0.25 of 9. That should make sense. Could you? We're looking for that, so starting at the mean, we want to be 0.25 standard deviations below the mean, so that's 0.259 below the mean. Yeah?
Even though it's below, you're still just adding it, right? So you're going to get a negative.
Oh, so if you wanted to use plus and minus like this?
Yeah.
Either way, so you can think of going below means minus or adding the opposite of the z, yeah, adding the actual z-square. Yeah, so two ways. You can just do add, or you can say, okay, I'm going to go below, so I'm going to subtract 0.25 standard deviations of the mean. And what do you got when you do that? 50.75 minutes. So if someone ran 58.75 minutes in this race, they're in the 40th percentile, which means they beat 40% of the other runners. Of all the runners, and 60%, or not beat. Sorry, they were faster than. Yeah, no, they were slower than. Right? These are finish times. So this person was slower than 40% of the field and faster than this 60% of the field. Okay, questions on that? So for time's sake, let's see. How's percentile? Okay, so let's one more thing. Let's do quartiles. So quartiles are just you're breaking up all the data into quarters. So it's going to be what will this be? So this would be 25%, 25%, 25, and 25. So this is Q1, Q2, Q3. So what percentile is quartile Q1, the first quartile? What percentile is that? 25%, the 25 percentile. What percentile is Q2? That's the 50th percentile. And what's that the same as? The mean, right? So the mean is the 50th percentile. And what's Q3? 75 percentile. Okay, so we're going to start, where are we going to look in the chart first? Do we have z-scores? If we're talking about taking percentiles and finding values, do we have z-scores or do we have areas? We have areas, right? So we're going to start with areas. We're going to start in the middle and get the corresponding z-scores. So let's just do, let's do this one. Let's do the third quartile for this particular data set. So for the third quartile, you're going to look at what in your z-chart? If it's the 75th percentile. What will you look at? Point what? 7500. Okay? What's the one that's closest to 0.7500 in your chart? 0.67 is the z-score for that. Agree? Is that the closest one? So what does it mean? It means for cholesterol level that, or for anything actually, so that means that if the observation that's 0.67 standard deviations above the mean will have a greater cholesterol than 75%. In this case, is of women. Okay? So our mean is 206. And our standard deviation is 44.7. So how would you find what cholesterol level is 0.67 standard deviations above the mean? Do you know how you would do that? So we need 0.67 of these, right? 0.67 of these. And what will we do with that? We're looking for then the observation that's 0.67 standard deviations above the mean. We'll take 0.67 of these and add it to 206. Were you all thinking that? I hope you're all thinking that. So we're going to take 206 plus 0.67 of 44.7. It's all about what that z-score means. It's a number of standard deviations. So we want that many standard deviations of, in this case, one standard deviation is 44.7. What do you get? Click. As soon as you get it. 235.95. So a woman with a cholesterol of 235.95 is at the 75th percentile. 75% of women have a lower cholesterol level than that, and 25% have a higher cholesterol level. Okay, any questions before we take the quiz? Yeah?
I'm still not doing it.
Okay, you just have to find the corresponding z-scores and then find the area. So do you remember how to find the z-scores?
I'm just really confused in the last.
Okay, so did you see this example about the IQ? Did you understand this example? So we've done all this thing with areas of z-scores, right? And so the point is that all we need to do is find the z-score for that, and the z-score for that, and then it's like all the other ones we've done, you just find the area between those z-scores. And then so z is your observation minus the mean over the standard deviation. So this one will be the observation, 115, minus the mean is 100, over 16 is your z-score for 115 IQ. And your z-score for 140 IQ is 140 minus 100 divided by 16. Do you remember that formula? We learned that, like, we've been doing that for a week or two. And so now that you have those z-scores, then you're just going to use the chart, and you get the area between those. Will be the same as the relative frequency between those two IQs. Because that area is the same as the area on the standard normal between these two z-scores. Does that make sense? So you just need this first step of finding your corresponding z-scores, and then it's like all these other examples we did today. We're going to take a quiz now. Okay, so maybe there's confusion about this last one. We'll just do it. Everyone will get 100 on the quiz, and we'll just do that last one. That's okay.
Okay, I just had a question, like, example.
But this isn't the right time to do that. I was about to hand out the quiz, so we'll just. Okay, where is it? Okay. Okay, so it said that of 117 students, it was normally distributed with a mean of 68. And a standard deviation of 12. Okay, so add 1, we get 80. Add 2, we get 92. Add 3, we get 104. Subtract, we get 56. Subtract again, we get, what is that? 44, and then 32. Okay, so we want the percent of students between 70 and 80. So 70 is right here, and 80. So the percent of students, how does that relate to this diagram? So what's our relationship between the percent of students between those two scores and this diagram? What's that relationship? Area, right? So that's what we've been saying. That the area there will be the same as the percent of students between a 70 and an 80. So how are we going to get that area? That area is the same as the area, what? On which curve? The standard normal curve, right? It's the area, it's the same as the area on the standard normal curve between what two values? Oh, no, well, not necessarily 0 and 1. So we need to figure out what the corresponding z-scores are, right? So there's some z-score that's just greater than 0 here that corresponds to a score of 70. And then there's a z-score, so 80 is 1 standard deviation above. So then that, we don't even need the chart for that because we know a score of 80 is 1 standard deviation above the mean. So that's z equals 1. So what do we need? We need the z-score for a score of 70 on the test. So what's the z-score for a score of 70? Everyone find, how would you find the z-score with this mean of standard deviation? What's the z-score for a score of 70? Right? Everyone do it. And divided by 12. 0.167. So what do we got? We got a z of 0.167 and a z-score of 1. So we didn't have to do the 1 because we found out that 80, a score of 80, that was exactly 1 standard deviation above the mean. So that's a z equals 1. Okay? So we've got our z-scores of 0.167 and 1, and now we want to find the area between the two, and I think that went pretty well, right? So everyone find the area between 0.167 and 1. What is it? Which is that's the final answer, or what is that? So let's get. So what is the area for 0.167 to the left? What'd you get for that from the chart? Oh, so we need to round that. So round this to 0.17. Okay, so we can use the chart. Just round it to 0.17. 0.5675. Someone else get that? And z equals 1. 1.00. What's the area to the left of that? Confirmation on those two numbers. Are we good? So the area between a z-score of 1 and a z-score of 0.17 is? 0.2738. Therefore, what percent of the students had a scores between 70 and 80? 27.38%. 27.38%. Why? Because the area between 70 and 80 is the same as the area between z equals 0.167 and z equals 1, which we can get from the chart. And that area is then the relative frequency. Questions on part A? Good? Okay, how about part B? So part B, we want the probability that a randomly selected student has a test score below 60. Set this thing up again. What's our mean? 68. So here's our test score of 60. So relative to this picture, what are we asking? The probability that a randomly selected student will have a test score lower than 60. What are we asking there? Relative to this picture. We're asking for what? He wants the area to the left of 60. Yeah, the area to the left of 60 would be the percent of all observations or all test scores less than 60, so that's also the probability. So how are we going to use our chart? We're going to go in our chart and look for z equals 60? What are we going to look for? We got to get the z-score, and the z-score is? Negative 0.67. And that gives us, that's our z-score, and so then the area is 0.2514. And so that's the area to the left of negative 0.67 on the standard normal curve. So how do we use that to find our area to the left of 60 on our curve? It's the same thing, right? Areas are the same. So the area to the left of 60 on our normal curve is the same as the area to the left of negative 0.67 on the standard curve, right? The areas correlate by standard deviation. So, probability that randomly selected student will have a test score below 60. .25, or about a quarter of the students we expect to score below 60. Okay, any questions on that? Okay, have a great weekend. Homework's due Sunday night.